If the universe is a single block of history, then by what authority does anyone decide where now is? This is the question gravity refuses to answer the same way twice. In 1908, Hermann Minkowski told a German audience that space and time were doomed to fade into mere shadows. The two, he said, were one fabric. Half a century later, three Americans, Arnowitt, Deser and Misner, tried to cut that fabric. To turn the four-dimensional whole back into something resembling the world we experience, they sliced it into three-dimensional sheets, stacked like the pages of a book. Each page was space at a single instant. They called it foliation. The cuts can be made in infinitely many ways. There is no preferred page. There is no engraved edge separating your past from your future. The line is drawn by geometry. Geometry is drawn by gravity. And gravity does not produce one line. It produces a shifting, twisting boundary that depends on where the observer stands, how fast they move, and how much mass sits between them and the rest of existence. By the end of this video, you will understand the mathematics that turns space-time into pages, the ADM formalism, what the block universe theory actually claims, why presentism versus eternalism is not a draw but a verdict, what the growing block universe explained really proposes, and what Wheeler and DeWitt found at the deepest level of quantum gravity. If you find value in explorations like this, in understanding the deep puzzles that keep physicists awake at night, consider subscribing to the channel, which helps these deep dives reach more curious minds. Now, let us begin. There is a thought that occurs to almost everyone, eventually, and then gets dismissed because it cannot be reconciled with the day that follows it. The thought is this: right now, on this side of the world, it is whatever hour it is for you. On the opposite side of the planet, it is a different hour. On Mars, the local clocks read something else entirely. And out beyond the orbit of Neptune, at the edge of the Kuiper belt, the very meaning of the word now has begun to drift. A signal from there takes hours to reach us. By the time we hear it, the moment it described has aged. We agree, by convention, to call all of these instants the same instant. We say it is now everywhere. But the word now does not survive the conversion. In ordinary life, this is a curiosity. In physics, it is the central problem of the 20th century. And in general relativity, where gravity itself shapes the cloth of space and time, it has a precise technical name. The problem is the problem of space-time foliation. The procedure for naming a now, anywhere and everywhere across the universe, is the procedure for choosing a foliation. There are infinitely many such procedures. None of them is the correct one. They are all, in the language of the field, gauge choices. Space-time foliation is the operation that takes a four-dimensional manifold, 3 dimensions of space, 1 dimension of time, all bound together by a single metric, and decomposes it into a one-parameter family of 3-dimensional surfaces. Each surface represents space at a single moment. The parameter is the time coordinate. The family fills the manifold completely. The leaves do not intersect. The picture you should hold in your mind is a loaf of bread, sliced not yet by any knife. The slices exist in the abstract. The geometry of the loaf permits them, But the knife has not chosen which direction to cut. And the knife, in general relativity, is the observer. Any world line through the manifold can supply its own slicing. None has priority. Hermann Minkowski was the first to argue formally that this was the right way to think. In 1908, in a lecture at Cologne titled simply Space and Time, he opened with words that have outlived almost everything else physics said that year. Henceforth, he declared, space by itself and time by itself were doomed to fade away into mere shadows, and only a kind of union of the two would preserve an independent reality. He was speaking about special relativity. The point was this: two observers in relative motion will disagree about which events are simultaneous. The disagreement is not a measurement error. It is structural. If we boost an observer to half the speed of light, the events they call simultaneous slope across the space-time diagram at an angle. They are not the events the stationary observer calls simultaneous. Both are right, both are wrong. The correct picture is not the slices. The correct picture is the four-dimensional union, the block they slice through. This is the origin of what philosophers and later physicists came to call the block universe theory. The claim is straightforward. The past, the present, and the future are all equally real. They coexist as features of a single four-dimensional structure. The flow of time, the sense that one moment becomes another, is not a property of the block. It is a property of how a conscious observer scans through the block. Einstein himself, in the last year of his life, wrote a letter of condolence to the family of his old friend Michele Besso. The letter contained a passage that has been quoted in nearly every popular book on physics since. People like us, he wrote, who believe in physics, know that the distinction between past, present, and future is only a stubbornly persistent illusion. He died 3 weeks later. The line is sometimes used as a piece of melancholy comfort. In context, it is a statement about the structure of space-time. The block is fixed. The illusion is the flow. We will return to that sentence in the third part of this video. The reading I am offering you now is the consensus reading among working relativists. It is not the only one. Now consider what happened next. Special relativity had handed physics a four-dimensional block. The block was flat. The metric was simple. Slicing it into nows was a matter of choosing a velocity. But Einstein had not yet finished. In 1915, he published the field equations of general relativity. The block now had curvature. Mass and energy could bend it. Light, which had previously travelled in straight lines through Minkowski space, now followed geodesics that curved around stars. And the act of slicing, the act of foliation, became dramatically more delicate. In flat Minkowski space, two observers boosted relative to each other simply tilted their notion of simultaneity. The tilt was uniform. Everywhere in the universe, the slice was tilted by the same angle. In a curved space-time, the tilt is no longer uniform. It varies from point to point. The slice can bend. The slice can warp. Near a massive body, the slice can be pulled out of shape so dramatically that what looks like a simultaneous instant on one side of the gravitational well is a different epoch entirely on the other side. The geometry of the slicing carries the geometry of the gravity. This is what the title of this video means. Gravity does not merely warp the space your body occupies, it bends and stretches the line that separates your past from your future. The line is not a metaphysical boundary, it is a hypersurface. It can be pushed and pulled by mass. The boundary between what has happened to you and what is going to happen to you is, in the strictest mathematical sense, a thing gravity can act upon. To make general relativity computable, physicists needed a procedure for splitting the four-dimensional equations back into something that looked like ordinary physics. Ordinary physics has a now and a next. You specify the state of the world at a single instant, and the laws tell you what the next instant will look like. This is the initial value formulation of physics. It is how Newtonian gravity works. It is how electromagnetism works. It is how quantum mechanics works. General relativity, in its native four-dimensional form, did not look like this at all. It was a self-consistent geometric object. It did not naturally distinguish a present from a future. In the late 1950s and early 1960s, three American physicists set themselves the task of fixing this. Their names were Richard Arnowitt, Stanley Deser, and Charles Misner. They published a series of papers across those years, culminating in a long monograph in 1962 in the Witten volume titled Gravitation, An Introduction to Current Research. Their work is known to every relativist today by the initials of their surnames. It is the ADM formalism. It is, without exaggeration, the language in which most modern computational gravity is written. What did they do? They took the four-dimensional metric of space-time, the object Einstein wrote down, and they rewrote it as a stack of three-dimensional metrics, evolving from slice to slice. The four-dimensional object became a three-dimensional object plus, a recipe for how to get from one three-dimensional object to the next. The recipe involved two new fields. One they called the lapse, the other they called the shift. The lapse, written as the function n, told you how much proper time elapsed between adjacent slices at each point in space. The shift, written as the vector field n to the I, told you how the spatial coordinates on one slice were related to the spatial coordinates on the next. In adapted coordinates, the line element of spacetime in the ADM split reads as follows. The interval ds squared equals gamma sub a b times the quantity dx to the a plus n to the a dt multiplied by the quantity dx to the b plus n to the b dt minus n squared dt squared. The gamma sub a b is the three-dimensional metric on the slice. The n is the lapse, the n to the a is the shift, the dt is the coordinate time interval between slices. Spoken aloud, the formula is straightforward. Spoken in plain English, it is more striking. What the formula says is this. The single four-dimensional metric, the geometric object that Einstein gave us, has been decomposed into three pieces. There is the geometry of the slice itself. There is a number that says how much real time elapses as you cross from one slice to the next. There is a vector that says how the slice slides sideways as you cross. And critically, both the lapse and the shift are arbitrary. You, the physicist, choose them. They are not specified by the equations of the theory. They are gauge. Think about that carefully. The equations of general relativity, when written in ADM form, contain four arbitrary functions of space and time, the lapse and the three components of the shift. You may pick them however you please. Each choice corresponds to a different foliation. Each choice gives you a different set of slices through the same four-dimensional manifold. The physics is unchanged. The events are the same. The geodesics of test particles are the same. What changes is the bookkeeping. What changes is what you call now. There is an experimental analogy that I want you to consider because it will recur. Think about a baker slicing a loaf of bread. The loaf is a four-dimensional thing in our analogy, frozen in shape. The baker holds a knife. The baker can cut horizontally, producing flat slices of uniform thickness. The baker can cut diagonally, producing oblong slices. The baker can cut along an undulating wave, producing ridged slices that follow some non-obvious contour. None of these cuts changes the loaf. The bread is the same bread. What changes is what the baker calls a slice. In general relativity, the universe is the loaf, the baker is the foliation, and the slices are the moments of time. There is no fact of the matter about which cut is correct. There is only a fact of the matter about the loaf. The ADM formalism took the four-dimensional Einstein field equations and split them in two. Some of the equations became constraints. They are conditions that must hold on each individual slice, restricting which three-dimensional geometries are even allowed. The other equations became evolution equations. They tell you how the three-dimensional geometry on one slice transforms into the three-dimensional geometry on the next slice. Of the constraints, there are four. One is called the Hamiltonian constraint. The other three together are called the momentum constraint. The Hamiltonian constraint is the equation that in vacuum reads R superscript 3 plus K sub ij, K to the ij minus K squared equals 0. The R superscript 3 is the three-dimensional Ricci scalar of the slice, the intrinsic curvature of the slice considered as a three-dimensional object in its own right. The K sub ij is the extrinsic curvature, the way the slice is bent inside the higher four-dimensional manifold. The K, with a single index on top, is the trace of the extrinsic curvature. The equation is a single nonlinear condition that must be satisfied at every point of every slice. It is, in a meaningful sense, the law of gravity for the geometry of a single instant. The momentum constraint, written with a covariant derivative, reads d to the j of k sub aj minus gamma sub ajk equals 0. Loosely speaking, it enforces consistency between how the geometry of the slice varies across space and how it is embedded into the four-dimensional whole. If you specify an initial slice with a three-dimensional metric and an extrinsic curvature fails to satisfy these constraints, no space-time exists. The data is inconsistent. The block does not close on itself. The slice is not a possible page in any possible book. This is the first concrete sense in which gravity restricts foliation. You might think any way of slicing space is allowed. In general relativity, it is not. The dynamics of the theory carve out which slicings are admissible and which are not. Gravity carves the geometry of the slice itself. Now, here is the part that will matter later. The ADM equations preserve the constraints under evolution. If you start with a slice that satisfies the Hamiltonian and momentum constraints, and you evolve forward according to the evolution equations, the constraints continue to hold on every subsequent slice. The constraint surface is a stable subset of the configuration space. It is not a knife-edge balance. It is a structural feature of the theory. This means that initial data, once given, propagates self-consistently across the slices. The universe stays geometrically lawful. But the data must be given. Somebody or something must specify the initial slice. The equations of general relativity do not tell you what slice the universe started on. They only tell you how to evolve forward, given an initial condition. The choice of initial slice is, in the precise sense used by mathematicians, free data. It is something the theory takes as input, rather than producing as output. Keep that in mind. We will need it. There is a name for the slices that admit this kind of consistent evolution across the full manifold. They are called Cauchy surfaces. A Cauchy surface is a space-like hypersurface that every inextendable causal curve in the space-time crosses exactly once. If a space-time admits a Cauchy surface, the space-time is called globally hyperbolic. The theorem you need to know was proved by Robert Geroch in 1970. A space-time is globally hyperbolic if and only if it can be smoothly foliated by Cauchy surfaces. Global hyperbolicity is the technical condition under which general relativity gives you a deterministic theory. Specify the data on one Cauchy surface, the future is uniquely determined. The past is uniquely determined. The universe behaves. When a space-time fails to be globally hyperbolic, predictability fails. The interior of a rotating Kerr black hole, for example, contains a region called the Cauchy horizon. Beyond it, the equations of motion cease to determine the future from any initial slice. Kurt Gödel famously discovered in 1949 that there are solutions to Einstein's equations describing entire universes that contain closed time-like curves. Universes in which an observer can travel into their own past. Gödel's universe is not globally hyperbolic. It cannot be foliated at all. The slicing fails. Time, as a coherent global concept, fails. Roger Penrose conjectured in 1969 that the gravitational collapse of realistic matter never produces a naked singularity, only ones hidden behind event horizons. The conjecture is called cosmic censorship. It remains unproven. Stephen Hawking added a related conjecture about closed time-like curves called chronology protection. The proposal that quantum effects will always prevent the formation of time machines. Neither is established. Both are widely believed. Both, if true, ensure that the universe we live in admits the kind of foliation general relativity needs to function. If they are false, predictability breaks somewhere. This is the first reason I want you to take note of. The theory of gravity, as we have it, is a theory of how four-dimensional geometries evolve. The evolution is mathematically beautiful, but for the evolution to make sense, for there to be a now and a next, the space-time has to be sliceable. It has to admit a Cauchy surface. It has to be globally hyperbolic. The condition is not automatic. It must be assumed or proven or, in practice, checked. Picture a stage manager preparing a long, complex theatrical performance. The script has thousands of actors moving through hundreds of scenes. For the play to be performed at all, the stage manager must construct a sequence of cues. Each cue is a snapshot of the stage at one moment. Every actor must be somewhere when the cue fires. No actor may be in two places. No actor may be missing. The play is the sum of the snapshots. Without a coherent cue list, the play cannot exist. Space-time in general relativity is the play. The cue list is the foliation. The condition that the cue list can be constructed at all is global hyperbolicity. What does it mean that a theory of gravity is forced to assume its own audience can be seated in a coherent sequence before the play can even begin? The ADM formalism, with its lapse and shift, with its constraints and its evolution equations, with its requirement that a Cauchy surface exists, is the practical workhorse of numerical relativity. Every gravitational wave signal that LIGO has ever detected has been compared against a template generated by numerical simulation of binary black hole or neutron star mergers. Those simulations split space-time using the ADM formalism, or one of its modern descendants. The most common is the BSSN reformulation due to Baumgarten, Shapiro, Shibata, and Nakamura. The slicings used are technical things, with names like 1+log slicing for the lapse and gamma driver shift for the shift. The choice of slicing is not arbitrary in practice. Some slicings handle singularities gracefully, others crash the simulation. But it is arbitrary in principle. The physics does not care. On September 14, 2015, LIGO detected a gravitational wave signal designated GW150914. The merger of two black holes, roughly 29 and 36 times the mass of the Sun, at a distance of about 1.3 billion light-years. The waveform was matched against numerical templates computed across the previous decade by groups in Pretoria, Caltech, Rochester, and Göttingen. The match was within experimental error. The slicing those simulations used was a gauge choice. The wave the detector received was a physical fact. Both descriptions of the same event are correct. The slicing was the bookkeeping. The wave was the universe. Now, let me give you a personal example of how literally this slicing affects daily life. You carry, almost certainly, a device with a global positioning system chip. That chip computes your location by comparing the times stamped on signals arriving from a constellation of orbiting satellites. Each satellite carries an atomic clock. The satellites orbit at an altitude of approximately 20,200 kilometers. They move at roughly 4 kilometers per second. According to general relativity, their atomic clocks tick faster than identical clocks on the ground because they sit higher up in Earth's gravitational potential. The relativistic correction is approximately plus 45 microseconds per day. According to special relativity, their atomic clocks tick slower than identical clocks on the ground because they are moving. That correction is approximately minus 7 microseconds per day. The net result is that the satellite clocks gain about 38 microseconds every 24 hours, relative to a clock at sea level. If GPS engineers had not corrected for this, if they had simply assumed that all clocks tick at the same rate everywhere, your position fix would degrade by approximately 10 kilometers per day. Within a week, navigation would be useless. The system works only because every GPS satellite is operating with a slicing of space-time imposed by hand. The slicing is called Earth-centered inertial time. It is a particular foliation. It is one of an infinite number of foliations that the Earth satellite system could be using. The other foliations would yield equivalent physics, but only this one yields navigation that lines up with where you actually are. Think about that. Every car, every plane, every fishing boat that uses GPS is enacting a choice of foliation. The choice is hidden inside the software. The driver does not know. The pilot does not know. The captain does not know. They simply trust that the position is correct. The position is correct because somebody, decades ago, made a foliation choice and propagated it through the design. What does it mean that the most successful navigation system in human history is built on a gauge choice nobody outside the engineering teams ever sees? Let me give you another grounding example. In 1971, two physicists named Joseph Hafele and Richard Keating flew 4 cesium atomic clocks around the world on commercial airliners. They flew them eastward, then westward. They compared the readings against reference clocks held stationary at the United States Naval Observatory. The eastward clocks were predicted by general relativity and special relativity combined to lose approximately 59 nanoseconds. The westward clocks were predicted to gain approximately 273 nanoseconds. The measurements were within the experimental uncertainty of the prediction. The Hafele-Keating experiment cost almost nothing, a few plane tickets and some clock rental. And it established, in the most ordinary possible setting, that there is no universal clock. The eastward and westward airliners pass through different foliations of the same planet. They returned to the same place, having aged differently. The differences were nanoseconds. The principle was absolute. Two world lines through the same space-time experienced different elapsed proper times. The block universe theory has no problem with this. It says simply the world lines were different paths through the same block. The block does not care. Gravity Probe B, launched by NASA in 2004 and operated until 2011, tested something more subtle still. The mission carried 4 gyroscopes, each a polished quartz sphere about the size of a ping-pong ball, machined to be one of the most spherical objects ever produced by human industry. The deviations from perfect roundness were less than 10 nanometers. The gyroscopes were placed in low Earth orbit, oriented at a guide star, and allowed to drift. According to general relativity, the gyroscopes should precess by 2 effects. One is the geodetic precession, about 6,600 milliarcseconds per year, caused by the curvature of space-time around Earth's mass. The other is frame dragging, sometimes called the lens-Thirring effect, about 39 milliarcseconds per year, caused by the rotation of Earth literally twisting the space-time around it. Both predictions were verified to within experimental error. Earth is not just a mass. Earth is a rotating mass. Its rotation drags the local foliation along with it. The slices, near Earth, tilt and twist around the rotation axis. The universe in this tiny neighborhood is being stirred. I want to pause for a moment because the implication is unfamiliar. Frame dragging is a real effect, measured to acceptable precision by a real spacecraft. And it tells us that the geometry of space and time around a rotating body is itself rotating. The boundary between your past and your future, the slice you would draw to define your now, is being dragged sideways by the spinning mass of the planet you stand on. The drag is tiny. The principle is enormous. Mass does not just curve space, spinning mass spins space. And spin space is also tilted time. Picture a thick fluid in which you are immersed. You try to draw a flat line across the fluid. Somebody stirs the fluid with a paddle. The line you drew is dragged into a spiral. Your sense of where now is, the line itself, has been deformed by the motion of the matter around you. Frame dragging is precisely this, except the fluid is not water and the stirrer is not a paddle. The fluid is space-time. The stirrer is Earth. We are now ready to introduce a concept that will reappear many times. It is the concept that in general relativity there is no preferred slicing. There are infinitely many slicings, and any of them can be used. And the equations of the theory do not select one over another. This is sometimes called refoliation invariance. It is one half of the symmetry called general covariance. The principle that the laws of physics take the same form under any smooth change of coordinates. Different observers in different states of motion, in different gravitational potentials, sit on different slices. None of them is right. None of them is wrong. They are all gauge choices. The slice that is now for you is past for somebody else and future for somebody after that. The universe does not adjudicate. The philosopher might pause here. The physicist will press on. The block universe theory says, of course, there is no preferred slicing. The four-dimensional manifold is what is real. The slicings are just labels. The labels are useful for doing physics, but they have no fundamental status. Presentism, the rival view, says only the present is real. The past does not exist anymore. The future does not exist yet. There is a privileged slice, the now, and it is the slice the universe currently occupies. This view is intuitive, matches how we feel. It is also, in the context of relativity, almost impossible to make coherent. The block universe theory wins by default in the working physics community, not because anyone has run a decisive experiment, but because the alternative requires a preferred slicing that relativity says cannot exist. There is a third option, less famous but worth introducing because it will matter in the final section of this video. It is the growing block universe theory, sometimes shortened to GBU. It was originally proposed by the British philosopher Charlie Dunbar Broad in 1923 in a book called Scientific Thought. Broad's proposal was simple. The past is real. The present is real. The future does not yet exist. Reality is a block, but the block is growing. As time passes, new slices are added to the growing edge. The future is not yet there. It is a region of non-being into which the block extends, one moment at a time. The growing block universe, explained in plain terms, is the proposal that the block is alive, that time is the construction of fresh existence at the leading face of being. The growing block universe is more intuitive than the static block universe theory. It captures the sense that there is a direction to time, that the past is fixed, but the future is open. It was developed in detail by the philosopher Michael Tooley in his book Time, Tense and Causation in 1997. It has a small but persistent following among contemporary philosophers of time. It has a problem. The problem is the same problem Presentism has. The leading edge of the block, the now where new slices are being added, has to be defined somehow. It has to be a specific hypersurface. But relativity says there is no preferred hypersurface. Two observers in relative motion will disagree about which slice is the present, which slice is the edge, which slice is the future just beyond the edge. The growing block universe needs a preferred foliation. Relativity will not give it one. We are going to come back to all three views: the static block universe theory, Presentism versus Eternalism, and the growing block universe explained in the final section. I am asking you, in the meantime, to hold the three positions in mind, neutrally, the way a juror is asked to hold testimony before deliberations begin. Let me close part 1 with one more equation, the most famous in physics, written down in the form that anchors everything we have been discussing. The Einstein field equations, in their full form, read as follows. The Einstein tensor, G sub mu nu, plus the cosmological constant lambda, times the metric tensor, g sub mu nu equals 8 pi g over c to the fourth times the stress-energy tensor T sub mu nu. The Einstein tensor encodes the curvature of spacetime. The cosmological constant accounts for the late-time acceleration of the universe's expansion. The metric is the geometry of spacetime itself. The stress-energy is the distribution of matter and energy. The constant out front, 8 pi g over c to the fourth, sets the conversion rate between matter and curvature. It is an absurdly small number, about 2 times 10 to the negative 43 in SI units, meaning that you need an enormous amount of stress energy to produce a noticeable amount of curvature. The Sun, by this conversion, curves spacetime around it just enough to bend a passing ray of starlight by about 1.75 arc-seconds, an effect first measured by Arthur Eddington during the solar eclipse of 1919. That equation, in the four-dimensional form, contains everything about gravity. It does not, however, contain anything explicit about time. There is no special time variable. The equation is symmetric across the time direction. It is invariant under arbitrary, smooth coordinate transformations, including reparametrizations of time itself. If you want to recover a notion of time, you must do the ADM split. You must foliate. You must choose a lapse and a shift. The equation does not tell you what to choose. The equation only tells you that whatever you choose, the constraints must be satisfied on every slice, and the evolution equations must be obeyed from one slice to the next. This is the situation at the end of part 1. The block exists. The block is real, or at least real-ish. That is the consensus among working physicists. The block is sliceable into nows in infinitely many ways. No slicing is preferred. Gravity bends the slices, mass twists them, rotation drags them. The boundary between your past and your future is, in the strictest geometric sense, a thing you can negotiate with the rest of the universe about. We will now go deeper. The deeper question is what happens when you take spacetime foliation seriously, all the way down into the regimes where general relativity meets quantum mechanics, and the regimes where the smooth manifold breaks. We have, so far, been speaking entirely within classical general relativity. That is the language Einstein wrote and Arnowitt, Desser and Misner refined. It treats spacetime as a smooth, four-dimensional Lorentzian manifold. At every point, the geometry is well defined. At every point, you could, in principle, stand and ask what the local light cone looks like, and which directions are time-like and which are space-like. The slicing is local, then patched across the manifold. The constraints hold at every point. The evolution proceeds smoothly. In the late 1960s, two American physicists asked whether this picture survives when quantum mechanics is taken into account. The physicists were John Archibald Wheeler and Wheeler-DeWitt. Wheeler was a Princeton theorist who had spent decades trying to find the simplest possible formulation of physics. He had coined the words black hole, wormhole, and quantum foam. He had a habit of writing down equations on cocktail napkins and leaving them for younger theorists to work out. DeWitt was a younger physicist trained at Harvard, working at the University of North Carolina, who took on the task of writing down the quantum version of general relativity in canonical form. The canonical version of general relativity is essentially the ADM formalism, but treated as a Hamiltonian system. The Hamiltonian of a system in classical mechanics is the generator of time evolution. The Hamiltonian of general relativity, when you do the ADM split carefully, turns out to be peculiar. It is not, like the Hamiltonian of a particle, a number representing the energy. It is a sum of constraints, the Hamiltonian constraint and the momentum constraint, each multiplied by a Lagrange multiplier, the lapse and the shift respectively. The Hamiltonian of general relativity is, as we say, weakly zero. It vanishes on the constraint surface where the physical solutions live. When you try to quantize this, to write down the equation for the wave function of the universe, you get something dramatic. The Schrödinger equation in ordinary quantum mechanics reads I times h bar times the partial derivative of psi with respect to t equals h hat acting on psi. The left side has an explicit time derivative. The right side has a Hamiltonian operator acting on the wave function. Time evolution is unitary. The wave function changes from moment to moment. In canonical quantum gravity, the corresponding equation is h hat acting on capital psi equals 0. The time derivative is gone. The Hamiltonian operator acts on the wave function and yields 0. This is the Wheeler-DeWitt equation. It is, in plain English, an equation in which time does not appear. I want to repeat that because it is the kind of statement that makes physicists uncomfortable, and many physicists prefer to qualify it heavily before letting students see it. The Wheeler-DeWitt equation, the central equation of canonical quantum gravity, contains no explicit time variable. The wave function of the universe does not evolve. It simply is. This is sometimes called the problem of time in quantum gravity. There have been thousands of papers written about it. There is no settled solution. Various proposals exist. One proposal is that time is an internal variable, that within the spatial geometry encoded by the wave function, some particular degree of freedom can be designated as a clock, and the apparent dynamics of the rest can be measured against it. This is the relational approach. Another proposal is that time emerges semi-classically, that for large-scale, low-curvature regions of the wave function, an approximate Schrödinger equation can be recovered, with the cosmic time of the surrounding spacetime acting as the time variable. This is the Born-Oppenheimer approach to quantum gravity. A third proposal, due to Don Page and William Wouters in 1983, treats time as a correlation between two subsystems, the clock and the rest. In all of these, time is something that has to be reconstructed, not something the fundamental equation provides. Karol Kuchar, a Czech-born physicist who spent his career analyzing this issue, identified 8 different facets of the problem of time, 8 distinct ways that time appears or disappears at different stages of the canonical formalism. None of them, he showed, is unambiguously the time we experience. Kuchar passed away in 2000. The facets remain unresolved. The Wheeler-DeWitt equation is the canonical quantization of the Hamiltonian constraint. Quantizing turns the constraint into an operator acting on a wave function. The wave function is a complex-valued function on the space of all possible three-dimensional geometries, a space sometimes called superspace, a word that has nothing to do with supersymmetry despite the coincidence. The wave function of the universe is a function on superspace. It is not a function of time. It is not a function of position. It is a function of the entire geometry of three-dimensional space. And the equation it satisfies has no time variable. The wave function does not change. If you take this seriously, the implication is unsettling. The universe, fundamentally, does not flow. There is no underlying clock. There is only a static, timeless wave function over the space of geometries. The clocks we use, the seconds we count, the years we age, all of these are derived constructions, reconstructed within the wave function, not part of its fundamental description. Julian Barber, the British physicist who has worked on this for decades, has written that time is, in a precise sense, an illusion. His book, The End of Time, published in 1999, develops this picture in detail. Barber argues that the universe is a vast collection of timeless moments. He calls them nows, and that what we perceive as the flow of time is the structural relation between these nows. There is no river. There are only points in the lake of all possible configurations. Each point includes within it the memories and the records and the apparent history of the others. The illusion of flow comes from looking at one now and seeing within it the records of others. Barber calls this his proposal of time capsules. It is speculative. It is also a serious attempt to take the Wheeler-DeWitt equation at face value. Picture, if you can, a museum that has been arranged with great care. Every room contains a snapshot of some moment in human history. The visitor walks from room to room. In each room, the visitor sees photographs, artifacts, written records, descriptions of the moments before and after. The visitor experiences a sense of history, of progression, of one room leading to another. But the museum itself is not moving. The rooms are not flowing. The museum is a static arrangement of static rooms. The progression is in the visitor, not in the museum. Barber proposes that the universe is something like this museum. Each now is a room. Each now contains the records of the others. The flow we experience is the flow of our attention through the static arrangement. What does it mean that the central equation of quantum gravity contains no time? There are essentially two answers. One answer says that the equation is incomplete, that we are missing something, that the right formulation of quantum gravity will restore a time variable, that the Wheeler-DeWitt equation is a stepping stone rather than a destination. The other answer says that the equation is right, that time really is emergent, that the universe is timeless in its deepest description, and that we are forced to live with that conclusion. Working physicists do not agree on which answer is correct. The field is split. The split is not, however, between credentialed scientists and the philosophically excitable. The split runs through credentialed scientists. Carlo Rovelli, an Italian physicist who has spent decades on loop quantum gravity, has written multiple books arguing the second view, that time is fundamentally an illusion, an emergent feature of statistical mechanics, rather than a basic ingredient of nature. Lee Smolin, a Canadian theorist who worked with Rovelli for years, has written books arguing the opposite, that time is the most fundamental thing in physics, more fundamental even than space, and that the timeless picture is wrong. The disagreement is sharp. It is also unresolved. Let me ground this in a specific historical fact. The first formal derivation of an equation having the form h hat psi equals 0 in the context of canonical quantum gravity appears in DeWitt's paper Quantum Theory of Gravity Part 1, published in Physical Review in 1967. The equation appears as equation 5.3 of that paper. It is buried in a long technical discussion of the canonical formulation. DeWitt did not call it the Wheeler-DeWitt equation. Nobody did at the time. The name was given later, after the equation had become central to attempts at quantum cosmology. Bryce DeWitt, in interviews late in his life, was modest about the equation. He once said, in essence, that he had not solved the problem of time. He had only written down the equation in which the problem of time first appeared in its sharpest form. He died in 2004. We will come back in Part 3 to the question of whether a timeless wave function is compatible with theistic or naturalistic interpretations. For now, hold the technical claim in mind. The deepest known equation of gravity contains no time. The fact is uncontroversial. The meaning is contested. Now let me turn to a related set of questions which have grown in prominence over the last 20 years. They concern foliation in the regimes where classical general relativity is strained, inside black holes, near the Big Bang, in the vicinity of singularities. In all of these places, the smooth manifold picture begins to break down, and the question of what slicing is appropriate becomes acute. Inside a Schwarzschild black hole, the simplest, non-rotating, uncharged black hole, there is a famous swap of the roles of space and time. Outside the event horizon, the Schwarzschild time coordinate, t, is time-like. The radial coordinate, r, is space-like. Inside the horizon, the situation reverses. The Schwarzschild t becomes space-like. The r becomes time-like. What this means physically is that once you have crossed the horizon, you no longer have a choice of direction in r. You must move toward smaller r. The singularity at r equals 0 is in your future. It is not a place, it is a time, a moment when, for any infalling observer, the geometry ends. The standard Schwarzschild foliation, using the t-coordinate, fails at the horizon. The slices fold up and cannot be continued through. Alternative foliations exist. The Painlevé-Goldstrand coordinates produce slices that smoothly cross the horizon. So do the Kruskal-Shekaresh coordinates. The horizon itself is not a singular feature of spacetime. It is a singular feature of the Schwarzschild slicing. Different slicings handle it differently. Inside a Kerr black hole, the more realistic rotating black hole, the situation is worse. There is an inner horizon called the Cauchy horizon, beyond which the predictability of general relativity breaks down. The interior of a Kerr black hole, in its idealized form, contains regions where closed time-like curves exist. An observer in those regions can, in principle, travel into their own past. There is no global foliation of the Kerr interior into Cauchy surfaces. The slicing fails because the space-time is not globally hyperbolic. The standard assumption that the space-time is sliceable does not hold. Penrose's cosmic censorship conjecture, in its strong form, says that the Cauchy horizon is unstable and will not exist in any realistic gravitational collapse. The conjecture is unproven. Some calculations suggest the Cauchy horizon is more stable than expected. The interior structure of realistic rotating black holes, the kind LIGO sees merging, is genuinely uncertain. We cannot foliate it cleanly. In cosmology, the situation is the opposite. The universe at large appears to admit a particularly nice foliation. The Friedmann-Lemaitre-Robertson-Walker metric, the FLRW metric, describes a universe that is, on large scales, homogeneous and isotropic. The natural foliation of an FLRW universe uses surfaces of constant cosmic time, which are the surfaces of constant density. The cosmic time foliation is sometimes called the co-moving foliation. It is the foliation in which the cosmic microwave background radiation is, on average, isotropic. Every observer at rest with respect to the cosmic microwave background sits on the same slice. They agree on what the universe looks like at the same moment. Now, this is striking. General relativity says there is no preferred foliation. The mathematical structure of the theory does not pick one. And yet, in our universe, the actual universe we live in, there appears to be a natural foliation given by the cosmic microwave background. Why? The answer is that the natural foliation is not picked by the theory. It is picked by the contents of the universe. The universe happens to be filled with matter and radiation distributed in a particular way, and that particular distribution defines a particular slicing. If the matter were distributed differently, if it were lumpy and non-isotropic, there would be no co-moving foliation. The natural slicing of our universe is contingent. It is a consequence of initial conditions and matter content. Other universes, with different contents, would foliate differently, or not at all. This is one of the most striking features of cosmology, and it is not stressed in popular accounts. The notion of cosmic time, the 13.8 billion years figure for the age of the universe, depends on the foliation we use. The number 13.8 billion years is the proper time along a co-moving world line from the Big Bang to the present. A different observer, moving relative to the cosmic microwave background, would measure a different elapsed proper time. The figure 13.8 billion years is universal only because we restrict attention to co-moving observers. Every press release that uses the figure is implicitly using the cosmic co-moving foliation. The number has no meaning outside that choice. What does it mean that the age of the universe is a foliation-dependent quantity, and that the foliation we have chosen is not picked out by physics, but by the happenstance of our matter content? There is another striking aspect. The FLRW metric describes a universe that begins with a singularity at cosmic time 0. The slicing fails at the singularity. The Big Bang is not a point in space, it is a moment in time, the past boundary of the cosmic time foliation. Every co-moving world line traces back to that singularity. The foliation does not extend beyond it. Whatever happened, if anything, at or before the singularity, is outside the domain of the foliation. The slicing has a first leaf. The block, if it is a block, has a beginning page. This is where the deep tension between classical general relativity and quantum gravity reappears. The classical singularity at the Big Bang is generally regarded as a sign that general relativity has broken down. The expectation is that quantum gravity will replace the singularity with something, a bounce, a tunneling event, an emergent classical region, but what that something looks like is not known. In loop quantum cosmology, the singularity is replaced by a quantum bounce. The universe contracts from a prior phase, reaches a minimum size, and re-expands. In the no-boundary proposal, due to James Hartle and Stephen Hawking, published in 1983, the singularity is replaced by a smooth, four-dimensional Riemannian region, a kind of curved hemisphere that has no boundary. The Hartle-Hawking proposal is a specific wave function for the universe, a specific solution to the Wheeler-DeWitt equation that imposes a particular boundary condition at the would-be singularity. In Hawking's popular book, A Brief History of Time, published in 1988, he wrote that the no-boundary proposal eliminated the need for a creator, that if the universe has no boundary, no edge, no beginning in the conventional sense, then there is nothing for a creator to do. The claim has been repeated many times since. We will examine it in Part 3. For now, note only that the claim depends on a specific choice of wave function, a specific boundary condition imposed by hand, and that the equation itself does not pick out that boundary condition. Different boundary conditions, equally consistent with the Wheeler-DeWitt equation, produce different wave functions. The choice is, in the technical sense, free. There is a similar story to tell in numerical relativity. When physicists simulate the merger of two black holes, they cannot simulate the singularities at the centers. The singularities have to be excised. They are cut out of the computational grid, and the boundary conditions are chosen to prevent information from leaking from inside the excision region to outside. The slicings used must be chosen carefully to keep the slices from crashing into the singularity. The 1 plus log slicing, developed in the early 2000s by Miguel Alcubierre and others, is a slicing that gracefully avoids the singularity by stretching the lapse to near zero near the trouble spots. The gamma driver shift smoothly transports the spatial coordinates away from the trouble spots. These are practical techniques. They make numerical relativity possible. They are also choices. The choice that allows you to compute is not the choice that the universe is making. The universe is not running a simulation. The slicing is human bookkeeping. The waves that reach LIGO are the universe's testimony. Several other approaches sharpen the same point. Causal dynamical triangulations developed by Jan Ambjorn, Jerzy Jurkiewicz and Renata Loll, builds quantum spacetime out of discrete four-dimensional simplices, but only produces something resembling smooth spacetime if a global foliation is imposed from the start. Without the foliation, the simulations produce degenerate geometries that do not look like spacetime at all. Horava-Lifshitz gravity, proposed by Peter Horava in 2009, makes time and space scale differently at high energies and, by construction, requires a preferred foliation, a kind of privileged time that the spirit of relativity is supposed to forbid. Shape dynamics, developed by Enrique Gomez, Sean Gribb and Tim Kozlowski, trades refoliation invariance for conformal invariance, fixing the slicing in exchange for a different gauge freedom. The pattern is consistent. To make quantum gravity tractable, the foliation freedom that general relativity insists on has to be broken, either by imposing a preferred slicing, or by trading it for another symmetry, or by accepting that time itself disappears from the fundamental equation. The classical block can be broken in many ways. The choice of how to break it shapes the resulting theory. Now let me bring all of this back to the three philosophical positions I introduced earlier. The block universe theory, sometimes called Eternalism, says that past, present and future are equally real, that the four-dimensional manifold is what exists, and that the slicing is observer-dependent and not fundamental. Presentism says only the present is real. The past has gone out of existence. The future has not yet come into existence. There is a privileged slice, the now, and only that slice contains anything. The growing block universe explained, also called the moving spotlight or growing universe, says the past is real, the present is real, the future does not yet exist, and the block grows as the present moves forward. Presentism is, as I mentioned, almost impossible to maintain in the presence of relativity. The argument was made formally by Hilary Putnam in 1967 in his paper Time and Physical Geometry. Putnam asked us to imagine two observers moving relative to each other, intersecting at a single event. According to presentism, only the present is real for each observer. But because they are moving differently, their hyperplanes of simultaneity tilt in different directions. Observer A's now intersects observer B's world line at a different event than observer B's now intersects observer A's world line. If only the present is real for each observer, then, by transitivity, all events on both world lines are real. The past of one is part of the present of another. The argument generalizes. With enough observers in enough different motion states, the union of presence covers the entire four-dimensional manifold. Presentism collapses into the block universe. Howard Stein responded to Putnam in 1968, defending a relativistic version of presentism in which only the present along a single world line is real. The reply has had defenders, but the cost is steep. Stein's presentism abandons the universality of reality. It becomes solipsistic in a way that earlier presentism was not. The mainstream view among philosophers of physics by the late 20th century was that Putnam had won. Presentism versus Eternalism was, in the relativistic context, a verdict for Eternalism, the block universe view. The growing block universe explained, as I mentioned, faces a similar but subtler problem. The growing edge of the block, the boundary where new slices are being added, has to be a specific hypersurface. But relativity provides no preferred hypersurface. Two observers in different states of motion will disagree about which slice is the edge. If observer A's leading edge is to the future of observer B's leading edge, then for B, A's edge contains events that do not yet exist. But A says they do exist. They are part of A's present. There is no way to make this consistent without giving up either the growing block's distinction between real past and unreal future, or the relativistic claim that no foliation is preferred. Most contemporary defenders of the growing block grant that the price is a preferred foliation, and pay it. They argue that the cosmic co-moving foliation is the metaphysically distinguished one. The argument is consistent. It is also philosophically expensive. We have already seen that the co-moving foliation is contingent. It depends on matter content. A metaphysics that picks out a specific physical foliation as the carrier of fundamental reality is wedded to a contingent feature of the universe. What does it mean that the philosophical position closest to common sense, that the past is fixed and the future is open, requires us to single out one of an infinite family of foliations as metaphysically privileged, on no basis other than that it happens to be the one our matter content provides? I want to drive one more grounding point before we move to part 3. The most successful test of general relativity in the strong field regime is the observation of gravitational waves from binary black hole mergers. As of the most recent LIGO-Virgo-CAGRA observing run, more than 90 such mergers have been catalogued. Each was extracted from the detector noise by matched filtering against a template bank, a pre-computed set of waveforms covering the relevant parameter space of masses, spins, and orbital configurations. The templates are produced by numerical relativity codes that solve the ADM-derived BSSN equations on supercomputers. Each waveform is the output of a specific gauge choice, a specific foliation of the merger space-time, propagated forward through tens of orbits, the final plunge, and the ring-down of the resulting black hole. The match between template and signal to within experimental precision is in itself a verification of the theory of general relativity and of the foliation method used to compute it. The slicings used are gauge choices. The agreement with observation is not. I want to pause and reflect. When I first learned about the Wheeler-DeWitt equation as a student, I remember thinking that surely the absence of time from the fundamental equation must mean that the equation is incomplete. There must be a missing piece. Time is, after all, the most basic thing in human experience. How could a theory of the universe leave it out? The years since have eroded that confidence. The more I have studied, the more it has seemed possible that the equation is telling the truth, that what we experience as time is something we are imposing on a fundamentally timeless reality, the way the visitor in the museum imposes a sense of motion on the static exhibition by walking through the rooms. I have not committed to that view. I do not know if it is correct, but I no longer find it absurd. It is one of the possibilities, and it has, as we will see in a moment, implications. We have now seen in some depth what spacetime foliation is, why it matters, how it works in the ADM formalism, how it fails in regions of high curvature, how it is replaced or supplemented by various quantum gravity proposals, and how it bears on the three classical philosophical positions about the nature of time. The block universe theory is the consensus among working relativists, not by virtue of any decisive experiment, but because the alternatives require structures, preferred foliations, distinguished hypersurfaces, that the theory itself denies. Presentism versus Eternalism as a live debate has been largely conceded in favor of Eternalism. The growing block universe explained remains as a minority position, defensible only at the cost of marrying a metaphysical claim to a contingent physical feature. We will now move to Part 3. We will return to the foreshadowed assumptions. We will examine the implications of all of this for the existence of time itself, the nature of human existence as a world line through a four-dimensional manifold, and the question of what or who would have to be true in order for any of this to make sense. Let us return to what we promised to examine. Earlier in this video, I quoted Einstein's letter to the family of Michele Besso, written 3 weeks before Einstein's own death in 1955. People like us, he wrote, who believe in physics, know that the distinction between past, present and future is only a stubbornly persistent illusion. The line has been used many times since to suggest that physics has discovered something inimical to religious belief, that the block universe rules out a creator, that the static four-dimensional structure leaves no room for divine action, that the absence of an objective now means no objective truth, and therefore no objective good. The line has been used to argue that free will is an illusion, that responsibility is a fiction, that the human experience of choice is a side effect of the world line our consciousness happens to be traversing. The line has been used in 1,000 books and lectures since as a kind of secular gospel, a piece of physics enlisted in service of a philosophical conclusion. I want to examine this claim. I want to examine it carefully in its strongest form with the fairness due to a serious position. And then I want to test it against the evidence. The claim, in its strongest form, has 3 parts. First, the universe is, on the consensus view, a four-dimensional block. All events exist tenselessly as features of that block. Second, there is no preferred foliation, no privileged now, no objective present. Third, the Wheeler-DeWitt equation contains no time variable, suggesting that at the fundamental level, time itself is emergent rather than basic. From these three premises, the strong claim concludes that human freedom is an illusion, that a creator is unnecessary because there is nothing for a creator to do, and that meaning, choice, and purpose are phantoms generated by our local perspective. This is a serious claim. It is held by serious people. Carlo Rovelli in The Order of Time, Hawking in A Brief History of Time, Sean Carroll in The Big Picture. The argument is not silly. It deserves a careful response. Here is the response. The first thing to notice is that the conclusion does not actually follow from the premises. Let me show you line by line why. The first premise says that the universe is a four-dimensional block. That is the block universe theory, and it is, as we have established, the consensus among working relativists. Fine, granted. The universe is a four-dimensional block. The past, the present, and the future are all equally real features of that block. Now ask the next question. Where did the block come from? The block is a structured, ordered, mathematically rich object. It satisfies Einstein's field equations everywhere. It contains a specific distribution of matter and energy. It exhibits a specific initial low-entropy state at the Big Bang singularity. It contains, embedded within it, the world lines of every star, every planet, every conscious being. The block is not nothing. The block is a maximally specific four-dimensional entity, with a precise geometry, a precise matter content, and precise boundary conditions. Why does that block exist rather than another block? Why does it exist rather than no block at all? The block universe theory does not answer this question. It cannot answer this question. The block universe theory is a description of what the universe is, given that the universe exists. It is not an explanation of why the universe exists. The premise that the universe is a four-dimensional block is silent on the question of the block's existence. The block, taken as a totality, is contingent. It could have been otherwise. It could have been nothing. A combination lock with 26 dials, each set to a specific value from 0 to 1 trillion, sits in front of you. The lock is opened. Inside the lock is a working universe. You ask how the dials were set. Someone tells you not to worry. The lock contains within it every state the dials have ever been in, every state they will ever be in, and a complete record of itself in the form of conscious word lines that perceive the dial settings as the laws of physics. This is true. It is also not an answer to the question. The question was how the dials were set. The answer was a description of the lock's internal structure. The description, however detailed, is not an explanation. The block universe theory, taken on its own, description of the lock's internal structure. It is not an explanation of why the lock exists at all, or why it has the specific dial settings it has. The fact that the lock contains records of its own configuration does not address the question of its origin. The question of the origin is logically separate from the question of the description. This is the first crucial point. The block universe theory does not eliminate the question of the universe's origin. It relocates it. Instead of asking why the universe began at the Big Bang, the question becomes why the four-dimensional block exists at all. The question has not gone away, it has been rephrased. It is, in fact, sharper than before, because now we are asking not about the cause of a temporal beginning, but about the ground of an entire four-dimensional structure. What does it mean that the most sophisticated picture modern physics has produced of the universe, the four-dimensional block of eternalism, leaves entirely untouched the question of why anything exists at all? The second premise says that there is no preferred foliation of the block. Granted, the mathematical structure of general relativity does not pick out a distinguished slicing. Different observers in different states of motion, in different gravitational potentials, sit on different slices, and the theory provides no way to declare one of them metaphysically primary. The claim that follows is that the absence of an objective now means the absence of an objective truth. This does not follow. The four-dimensional block, taken as a totality, is an absolutely objective fact. Every event in the block has a definite location, a definite time coordinate in any given foliation, and a definite relationship to every other event. The structure is absolute. What is observer-dependent is only the partition of the absolute structure into nows and laters. The structure itself is not observer-dependent. The geometry is not subjective. The block, as a four-dimensional object, is what it is. This is sometimes missed. The relativity of simultaneity is taken to mean the relativity of reality. It does not mean that. It means only that the way we cut up reality into temporal sequences is observer-dependent. The reality itself, the four-dimensional manifold, is something every observer agrees on. They simply describe it using different slicings. Picture a building. From the front, the building has a certain facade. From the side, it has a different facade. From above, it looks like a roof. Each observer, looking from a different angle, describes the building differently. Each description is correct from its viewpoint. The building itself is a single objective thing. The observer dependence of the description is not an observer dependence of the building. There is no inference from the multiple descriptions to the conclusion that the building is somehow less than fully real. The descriptions are partial. The building is whole. This is the situation with respect to the block universe and the relativity of simultaneity. The descriptions, sliced into nows, are partial. The block, taken as a totality, is whole. The block exists as a complete four-dimensional object. The slicings are how it is described, not what it is. The argument from no preferred foliation to no objective truth confuses the level of description with the level of the thing described. Now the third premise. The Wheeler-DeWitt equation contains no explicit time variable. The wave function of the universe does not evolve. Granted, the equation is what it is. The deepest equation of canonical quantum gravity is a constraint, not an evolution equation. Time, at the fundamental level, is not a basic feature. The claim that follows is that this eliminates the need for a creator. That, too, does not follow. In fact, the situation is the reverse. The Wheeler-DeWitt equation, taken at face value, presents a picture in which the universe is a single, timeless wave function over the space of three-dimensional geometries. The wave function satisfies h hat acting on capital psi equals 0. The equation is a single condition on the wave function. It does not specify which wave function. The space of solutions is enormous. There are countless wave functions that satisfy the constraint. The particular one that describes our universe is one specific choice out of this enormous space. Why that one? Why not another? Why any at all? The Wheeler-DeWitt equation, far from eliminating the need for explanation, actually clarifies it. The equation tells us that the universe, at its deepest level, is a specific wave function. The equation does not tell us why that wave function. The boundary conditions, the initial data, the choice of which solution out of the constraint space describes reality, none of these are picked out by the equation itself. They are inputs, not outputs. Whatever specifies them, whatever determines which wave function the universe is logically prior to the equation. This is a point that Hawking in particular obscured in his popular writing. The no-boundary proposal of Hartle and Hawking is one specific choice of wave function. It is a specific boundary condition imposed on the Wheeler-DeWitt equation. The equation does not pick it out. The proposal is a choice. Hawking advertised it as eliminating the need for a creator. But the proposal itself is a parameter set that has to be selected. The selection is not done by the equation. The selection is done by a hand that reaches outside the equation. Whose hand is it? There is no answer within physics. There cannot be an answer within physics. Physics describes the structure of solutions. The selection of which solution describes reality is a metaphysical question. It is the question of why this universe, this particular wave function, this particular initial state exists rather than another. The Wheeler-DeWitt equation does not answer it. The no-boundary proposal does not answer it. The Block universe theory does not answer it. The fundamental equation of quantum gravity is timeless, granted. But the timeless equation has timeless solutions, and the selection of a specific timeless solution as the description of our reality is itself a fact that requires an explanation. The fact that the wave function does not evolve does not entail that no explanation is needed. The fact that time is emergent does not entail that the wave function explains itself. A scribe writes down a single, timeless symbol on parchment. The symbol stands for the universe. The universe contains, embedded within its single symbolic form, all the world lines, all the histories, all the experiences of conscious beings that perceive time flowing within it. Ask why the scribe wrote this symbol and not another. Ask why the scribe wrote anything at all. The single symbol is an exhaustive description of the universe. It is not an explanation of why there is a universe. Replacing the unfolding history of the universe with a single, timeless symbol does not eliminate the question of why the symbol exists. It only changes the form of the question. What does it mean that the deepest possible description of physical reality, a timeless wave function satisfying a single timeless constraint, leaves entirely unaddressed the question of why that wave function exists rather than another or none at all? Now I want to bring in a structural argument that goes back to the medieval philosophers, the argument from contingency, and show how it applies here with new force. The argument, in its classical form, runs as follows. Every contingent thing, everything that could have been otherwise, everything whose existence is not necessary, depends for its existence on something else. The chain of dependence cannot regress infinitely without contradiction. Either there is a necessary being on which contingent things ultimately depend, or there is nothing at all. There is not nothing. Therefore, there is a necessary being. The argument is sometimes resisted on the ground that the universe itself might be a necessary being, that it exists by its own nature and does not require an external ground. The block universe picture sharpens the argument and makes that resistance harder to maintain. Here is why. The four-dimensional block of spacetime is not necessary in the sense the argument requires. It is one of an infinite family of possible four-dimensional structures. The Einstein field equations admit countless solutions. The Wheeler-DeWitt equation admits countless wave functions. Each is a possible universe. The actual universe is one particular member of this infinite family. The fact that it is this one and not another is itself a contingency. A necessary being, by definition, could not be otherwise. The block is otherwise. Countless alternatives are mathematically possible. Therefore, the block is contingent. The contingency cannot be removed by appealing to other blocks, or to a multiverse of blocks, or to a wave function over the space of blocks. Each of those structures is itself contingent in the same sense. Each could have been otherwise. The regress does not terminate within the space of possible physical structures. To terminate the regress, you need a being whose existence is necessary, not contingent. A being that exists by virtue of what it is, not as one selection among alternatives. The necessary being, by the structure of the argument, has several properties. It is not part of the four-dimensional block. It is not contained within any wave function. It is not a feature of any spacetime. It exists logically prior to spacetime, in the sense that the existence of spacetime depends on it and not the reverse. It is, in the most precise possible sense, timeless. The timelessness is not the absence of time, the way the Wheeler-DeWitt wave function is the absence of time. It is the priority over time. The necessary being is not in the block. The block is in the necessary being's act of grounding. Here is the striking thing. The timelessness implied by the contingency argument matches almost exactly the timelessness suggested by the Wheeler-DeWitt equation. but it explains what the equation leaves unexplained. The equation tells us that the universe at its deepest level does not contain time. The contingency argument tells us that the ground of the universe, whatever it is, must be timeless. The two are not in conflict. They point in the same direction. The Wheeler-DeWitt picture is compatible with, indeed naturally fitted to, a metaphysics in which the ground of being is timeless. Augustine wrote in the Confessions about the question of what God was doing before he created the world. The answer Augustine gave was that the question is malformed. Before God created the world, there was no before. Time itself is a feature of the created order. God does not exist in time. God exists as the eternal source of time, not as something that has its own clock. Boethius, in the 6th century, formalized this further. Eternity, he wrote, is the simultaneously whole and perfect possession of unending life. The eternal being does not endure through time, it possesses all of time at once. This is, in essence, the metaphysics that the Block universe theory describes from the inside. The universe as a totality, all moments present at once. And that the Wheeler-DeWitt equation hints at from the deepest physical level. The universe as a timeless wave function. The classical theistic conception of God is, by structural similarity, the natural ground for both. What does it mean that a metaphysical picture developed by medieval theologians, for reasons having nothing to do with general relativity or quantum gravity, fits the structure of modern physics more naturally than the metaphysical pictures developed by atheist philosophers in response to physics? The argument from contingency gives us a timeless necessary being. The argument from fine-tuning gives us additional properties. The block of our actual universe is governed by a small set of physical constants: the gravitational constant g, the cosmological constant lambda, the fine structure constant alpha, and others, that take values within an extraordinarily narrow range, compatible with the existence of stable matter, complex chemistry, and world lines that we would recognize as containing life. Change any of these by a fraction, and the block describes a sterile universe. Martin Rees, the former Astronomer Royal, devoted a book to just 6 of these numbers and called them tailor-made for life. The block we live in is, mathematically, one in a vast space of possible blocks. And it sits in a corner of that space where the geometry happens to permit the existence of beings who can ask why it is as it is. Picture a deck of 1 trillion cards. Each card describes a possible universe. The vast majority describe universes with no stars, no atoms, no stable structures. A tiny minority describe universes whose constants permit long-lived stars, the synthesis of heavy elements, planets, and the emergence of beings capable of reading the card. You shuffle the deck. You draw a card. The card you draw is one of the tiny minority. The question is not whether you drew a card. The question is why the card you drew is the one that permits you to be reading it. The standard naturalistic response is the multiverse, that the deck is shuffled infinitely many times in different regions, and we necessarily find ourselves in one where the constants permit our existence. This has problems. The multiverse is unobservable. no measurement can confirm or refute it. An entity that cannot in principle be tested is not a scientific claim. It is a metaphysical claim. And it does not solve the problem. Even granting an infinite multiverse, the mechanism that generates it must itself be tuned to produce universes at all. The contingency does not vanish. It recedes one level. The simpler explanation is that the block we live in is not a random draw. It is a chosen draw. The choice was made by the necessary ground of being, whose existence the contingency argument requires. The fine-tuning is the consequence of a choice. The choice was made with knowledge of the consequences. The choice was made with power adequate to instantiate the block. The choice was made with will, because a choice was made rather than no choice. Knowledge, power, will. These are the structural features any choosing being must have, derived from the structure of the choice itself. What does it mean that the deepest physical theory we possess, general relativity, with its block universe, its refoliation invariance, its timeless Wheeler-DeWitt formulation, is structurally most at home in a metaphysical framework that asserts a timeless, intelligent ground? One final piece of the strong claim deserves response. The claim that the block universe implies the loss of free will. If the future already exists, fixed in the block, then, the argument runs, no choice we make is truly open. We are simply traversing a world line that has been there all along. The sense of choosing is illusory. We are riding a rail laid in advance. This argument confuses determination with constraint. The block contains a fixed future, but the fixity is not by itself a constraint on the choices that constitute the future. The choices are part of the block. They are features of the block. The block is what it is because the choices are what they are. The relationship is not one of advance writing followed by later compliance. The relationship is one of mutual constitution. This is the standard compatibilist response to fatalism, sharpened by the block picture. It is also the standard theological response to the divine foreknowledge problem, going back at least to Boethius. Boethius observed that God's foreknowledge does not coerce the future because God does not see the future as future. God sees the totality of time at once, in a single, eternal act. The future for God is not yet to come, it simply is. The seeing does not cause the choice. The seeing is simultaneous with the being chosen. The classical doctrine of divine eternity, taken seriously, is precisely the structure that the block universe describes from the inside. The materialist who uses the block to argue against free will is borrowing a picture developed by theologians to support the very position the theologians constructed it to defend. The block is metaphysically neutral on free will. The argument that the block rules it out commits a category error. We have now examined the three strongest forms of the claim that the physics of space-time foliation is hostile to theistic belief. The first claim, that the block universe eliminates the need for a creator, fails because the block is contingent and requires a ground that the block itself cannot provide. The second claim, that the relativity of simultaneity destroys objective truth, fails because the block, as a totality, is objective, and the observer dependence is only of the slicing, not of the reality. The third claim, that the Wheeler-DeWitt equation makes a creator unnecessary by eliminating time, fails because the equation has a vast solution space and the selection of our specific wave function is itself an unexplained fact that the equation does not address. Each failure points in the same direction. The deeper physics goes, the more clearly it isolates the question of why there is something rather than nothing, and the less the language of physics can answer that question. Physics describes the structure of what exists. It does not explain why the structure exists rather than another structure, or no structure at all. The selection is logically prior to the description. The selection has properties. The selection requires a selector that is not itself part of the selected. The selector is timeless, knowing, powerful, and willing. The selector, by classical philosophical theology, is what every major monotheistic tradition has named. I want to be careful here. I am not arguing for any specific religious tradition. I am arguing only for the rational conclusion that the physical evidence, the block universe, the relativity of foliation, the timelessness of the deepest quantum gravity equation, the fine-tuning of the constants, the contingency of the actual configuration, points toward a necessary, timeless, intelligent ground of being. The philosophical name for this is classical theism. The structural argument is independent of any particular revealed tradition. The physical structure of the universe is consistent with, indeed naturally fits, the metaphysical framework that classical theism has been articulating for millennia. The fit is not coincidence. The fit is the consequence of both sides being responsive to the same underlying reality. What does it mean that 21st century physics, in its deepest theories, points back to a metaphysical structure articulated by theologians more than a millennium ago? That the doctrine of eternity, developed without telescopes or calculus, turns out to fit the structure of modern quantum gravity better than any picture sophisticated atheist physicists of our own century have produced. The block universe is not a problem for theism. The static four-dimensional manifold of eternalism, all moments coexisting tenselessly, is the structure that an eternal creator's view of creation looks like from the inside. The relativity of simultaneity is the consequence of a created order that is one whole, refracted into temporal sequences only by the perspectives of beings embedded within it. The timelessness of the Wheeler-DeWitt equation is the limit at which the description of the block approaches the eternal moment at which the block is held in being. The naturalistic argument is that all of this happens without anyone holding it. The static manifold simply is. The wave function simply is. The fine-tuning is coincidence. The contingency requires no ground. The existence requires no explanation. This is not a scientific position. It is a metaphysical position dressed in scientific vocabulary. The scientific evidence is consistent with it. The scientific evidence is also consistent with classical theism. The choice between them is not scientific. It is philosophical. And the philosophical case, when examined carefully, favors theism. The block points to its ground. The wave function points to its selector. The fine-tuning points to its tuner. The arrow of reasoning at each level points outward, from the physical structure to a non-physical source. Let me bring this exploration to a close. We started with a question about now. The question was, where, in a universe that physics describes as a four-dimensional block, anyone gets the authority to draw the line between past and future? The answer turned out to be more striking than the question. Nobody gets that authority. The line is not engraved in the block. It is drawn by each observer, in each motion, in each gravitational potential. And the line drawn by one observer cuts across the line drawn by another. The block universe theory describes a totality in which past, present and future coexist tenselessly. Presentism versus Eternalism, as a philosophical debate, has been largely settled by physics in favor of the eternal view. The growing block universe explained, as a third option, depends on a preferred foliation that relativity cannot supply. The mathematics of the ADM formalism, with its lapse, its shift, its constraints, makes computable a theory that does not pick a preferred slicing. The slicing is gauge, and gravity bends the gauge that any observer chooses. We followed this into the deeper structure. The Wheeler-DeWitt equation, the canonical version of quantum gravity, contains no explicit time variable. The wave function of the universe does not evolve. Time, at the fundamental level, is emergent, or absent, or hidden, depending on whose interpretation you favor. Numerical relativity makes practical use of foliation choices to compute the gravitational waves LIGO detects from black hole mergers a billion light-years away. The slicings used are choices. The waves are physical. The whole picture is consistent. The whole picture is also, when examined carefully, a description of structure that fails to explain why the structure exists. We then asked, in the third part, whether the block universe and the timeless wave function are hostile to theistic belief, as 1,000 popular books have suggested. The answer turned out to be the opposite. The block is contingent. Contingency requires a non-contingent ground. The ground must be timeless because time is internal to the block. The fine-tuning of the block's constants points to selection rather than chance. The selection points to a selector with knowledge, power and will. The Wheeler-DeWitt equation, far from eliminating the need for a creator, sharpens the question of why this particular wave function was selected from the vast space of solutions. The block universe, far from undermining theism, matches almost exactly the metaphysical picture that classical theism has been articulating since Augustine and Boethius. The deeper modern physics goes, the more its structure converges with the structure that classical theology developed independently. The strong materialist claim that the universe makes sense without an intelligent ground fails, not because the physics is wrong, but because the physics describes a structure that, by its own logic, requires a ground it cannot supply. The strong theistic claim that the universe makes sense as the work of a timeless, intelligent ground is the position the evidence points toward when the physics is read as it is, rather than through the lens of a prior commitment. If you found value in this exploration, in the patient examination of what gravity does to the boundary between your past and your future, consider subscribing. It helps these deep dives reach more curious minds. The block holds you, all of you, every moment of your life, laid out as a world line through the geometry. Somewhere outside the block, beyond every foliation any observer could ever draw, the ground of the block holds the block. The line between your past and your future is bent by the gravity around you. The block as a whole rests in something that gravity cannot bend. That something does not need to be sliced into nows in order to know you. It already does. Good night.